upgrade this one with some kind of interesting fudging. So the idea is the following. I now have only one database, which is initially encrypted and reshuffled. And the secure coprocessor may accesses out of this database C records. And the number C is predetermined but stays the same for every query. Okay? The secure coprocessor takes these C records, and one of the records is the requested one. The secure coprocessor accesses these C records, fetches the requested value, sends it back to the user, but before, and he does additional operation, he takes these C records, re-encrypts them, and writes them back, not at the same places, but randomly shuffled around again. So rather than doing the reshuffling as a pre-processing or intermediate processing step, you do a little bit of this reshuffling on the fly, always for these three C records. Okay? Everybody with me? Okay. So what's the likelihood for an adversary to say something about my result? Of course, it is it is known that one of the C records is one of the records requested. So I can observe as an adversary the positions, namely the positions here at this point, at this point, this point, this point, and this point, where I wrote back the accessed records. But I don't know which of the original are now positioned at which point in the slightly rewritten database. So I'm doing some fudging there. Okay. So if you take this basic algorithm, you can somehow track which records are accessed, where do they end up. You can do some probability counting, and you somehow can more or less track the probability of every record sitting at a particular position there. And if you do a lot of counting, you have to do it for every record. You have to recompute the probability after every query. It's a lot of bean counting, but you can do it. In order to do a little bit more confusion for the adversary, we introduce a slight variation. We add what we call something like a buffer or a pool that keeps a certain number of values from our database. So rather than writing all C values after re-encryption and reshuffling back into the database, we'll take one of the records, put it into our pool. With the same likelihood, we pick any of these records from our pool, and that's the victim that is written back instead of the one that we keep in the pool. Okay? So this pool is somehow a way to confuse even this kind of probability counting by the adversary even more, because the adversary now doesn't know anymore, is it one of the C records that I accessed in the database, or does the record come out of the pool? Okay. So the question you might ask is, what are all the techniques you are using in order to confuse the adversary? This is one of the several we tried out, and I will present in a second another one, and we haven't fully explored this space. These two, this is the first one I introduced, were quite successful because it makes it almost impossible for the adversary to learn something, meaning counting the probabilities, which record I can find at which position. Okay. So the requested record is either stored at one of the C positions that I accessed, or it still stays in the pool. And if that it stays in the pool, that's more or less the probability here. Okay. Notice, and I think I forgot to mention that one very important property of the last algorithm, also of this algorithm, is that with this kind of algorithm, you never can completely exclude any record to be the requested record. That's also very important. Every record has a probability greater than 0, meaning that the record can be in the resulting record. So what I want to show you with the next slide is something that I would call almost impossible. What we try to come up with is an analytical model, as I said, trying to count or trying to compute the probability for every record after every query with this kind of scheme. And forget about with this kind of scheme. So what I want to do is what really the adversary has to do. He has to determine every time what's the likelihood that a record stays in the pool or is written out to the storage media. So here I give you only an example of two records that the adversary might track. It's the record R8 and R44. So initially, that is the likelihood with the first query, independently whether or not the adversary asked this query or not. Remember, the adversary can also ask this query. The likelihood that this record stays in the buffer pool. So with the ith record, you can say what's the likelihood that R8 is still in the buffer. That's more or less this probability. And R8 is introduced new, and if you have another query, J, which is bigger than I, then you get other probabilities. So you have to do a lot of computation there. It's a lot, but it's complicated, but you still can do it. But there are some complications, and I will introduce another fuzzification factor that makes it almost impossible. At least we weren't able to do it. We actually introduced another somehow way. We introduced a so-called history list, which helps you to even make this computation even more complex from our point of view, even though we can't formally prove it impossible. That helps you to not only access possible answers from the pool, but also from the so-called history list. That somehow balanced out some imbalances that we recognized that there was a larger likelihood that certain answers could come from the pool rather from the media, and we try to balance this out. But these are somehow less important aspects. Let me focus here on this graph here. What I want to show here is the following. We wanted to see how much the adversary can learn from this kind of algorithm. And I hope you can distinguish, there are two lines, the red and the blue one. The red is more or less the probability that the user asks for a record A with query I. And the blue line is that the user asks for a record not equal to A with query I. And the difference is more or less what the adversary can learn. Well, that's what we can define, that he or she can learn. And if you see, these two lines, and this is more not done by an analytical solution, but really by simulation, that the difference is not there. I mean, sometimes the red line is over the blue line and vice versa. So what this really says is there's random noise. The adversary cannot really learn anything about it. This is under the assumption that you have this history list which really keeps, and I will show you in a second how this will continue, which keeps somehow these two, the blue and the red line, more or less on the same level. So this was for an artificially created database with 1 million records. The pool size was 10. C equals to 15. Don't ask me why my students used here the number 15, which sounds pretty high, but you can play with it. And the history size has also this very strange number, 383. So that meant the last 383 accesses were recorded in the history list. It was some kind of looking back into the past to see whether or not sometimes you can pick one of these values as well to outbalance things. And you will see why this is important. This is a similar kind of picture, but over more than the first 100 queries. You see it goes up, and that's the X line, goes up to 2,000 queries. So what happens is, here you can see the red, and in this case the black line, widen. There's a gap showing up. And that's happening at the point when you have exhausted the history list with 383 records. And so at that point, you see that the red line and the black line drift apart. And this is what I call that the adversary can learn about these two different possibilities. And if you look at the range of probability, that's really well below 1%. So it's really very little that the adversary can learn with the scheme given.